Okay, can you hear me? Good morning, everyone. Yes, I'm the new chief scientist for the Exoplanet Program. I've been here since February. I have a new deputy coming, Eric Mamajek, who's been at University of Rochester for a long time. So it's a whole new crew for science in the Exoplanet Program starting this year. And I want to tell you what the program does, why it does it, and remind you about ways that you can be involved. So I want to think ahead. Imagine that it's the 2030s, all right? And a big discovery comes across. And that discovery might look like this, that we have found a nearby star with a planet in its habitable zone. We've been able to measure the spectrum of that star and see that it has habitable conditions and that it even has disequilibrium in its atmosphere to indicate the presence of life. So I'm biased here in the sense that I'm calling it an imaging mission. JWST might get this sooner if things go really well, but we'll plan to have to do this with an imaging mission. So how are we going to make this goal happen? It's not going to happen by accident. It's going to require some planning and some focus and money. And so let's talk about what that problem is going to be to make this happen. So let's consider the nearby star 40 Eridani A. This is at 5 parsecs. It's a K-dwarf star, and it actually has a binary companion, B and C, off at about 80 arc seconds away. But that won't mess up our imaging experiment. That's far enough away. The habitable zone around this nearby star is very close, 0.13 arc seconds. If you use Hubble, you know the resolution of Hubble is about 0.05 arc seconds. So this is very close. And if an Earth mass planet is in that habitable zone, it's going to have a very small radial velocity amplitude, 12 centimeters a second. It's going to have a very low probability of ever transiting at 0.6 AU, where the habitable zone is. The astrometric wobble that it induces is going to be small. And it's not close to the galactic plane. It's not going to lens anything. So you've heard over the past few days about how our RV capability is at best 50 centimeters a second for some marginal detections. And that we don't have this astrometric capability now. How are we going to detect this planet? We can't detect this planet with our current capability. So that's a challenge and a goal. Today's the release date for Star Trek Beyond. And so the Exoplanet Program has a little feature about that on the website. 40 Eridani A is the purported host star by declaration of Gene Roddenberry for the fictional planet Vulcan. So as scientists, we're frustrated that we can't detect an Earth-like planet around a star this close. And I guess if you're a Star Trek fan, you're frustrated because you can't confirm that Vulcan is really there and that J.J. Abrams blew it in 2009 when he destroyed it. So let's see for both reasons if we can do better. So the imaging challenge for this planet is that it would be faint, but Hubble has looked at things much fainter than this. It's gone down to 30th magnitude in the deep fields. This would be a 27th magnitude planet when it's seen at elongation. Contrast to the star, 3 times 10 to the minus 10. And it would be separated by 3 resolution elements in the visual band if you were using a 3-meter telescope, so a little bit bigger than Hubble. So it's not crazy to talk about a telescope that'll resolve this. And if we do the imaging discovery of it, we can also characterize the planet's atmosphere by measuring its spectrum and the optical and hopefully the near-infrared too, and find out if there are these biological features to get us above the fold on the New York Times in the 2030s. Sooner would be better. All right, so how close are we to being able to do that in terms of the imaging requirements? I'm showing you here on the bottom some actual laboratory data that was taken in a vacuum tank up at JPL, a tank called the High Contrast Imaging Test Bed, where experiments are done to demonstrate the operation of coronagraphs down to these contrast levels. And so you can see here that if you look at a 1% narrowband pass, this region next to the star is at that position, is all showing dark blue, which on our contrast scale is down there at 10 to the minus 10. If you get a broader band pass, it's harder to make the contrast stay as good. Now it's getting up to like 6 times 10 to the minus 10. And 20% band pass, that's what astronomers like to observe in for V band or I band or something like that. The contrast is 2 times 10 to the minus 9. But you can see at least we're getting close to the ability to do this, and this was actually a result from back in 2012. So we're within reach of the contrast and the bandwidth that we need to do this, at least in terms of the coronagraph instrument. We have to make sure we can attach it to a telescope that's stable enough to do this experiment. So how does this experiment happen? How do we organize it? And how are we going to be organized for that goal of seeing biosignatures in an Earth-like planet in the 2030s? Well, that's what the Exoplanet Exploration Program is for. The community has said through its decadal surveys that the scientists want to see habitability of planets probed. It's resulted in all these great missions that you have heard about at this meeting and are working on data from. And so through the decadal surveys, NASA headquarters has made a science plan, and it is actually the policy of NASA's astrophysics division to discover planets around other stars, characterize their properties, and look for ones that could be habitable. So the Exoplanet Program is the organization at the Jet Propulsion Laboratory, a branch of NASA headquarters located at JPL, that is tasked with implementing the science plan for exoplanets and forming a vision for how we can implement the decadal survey's recommendations on a week-to-week, month-to-month level. All right, so what is not in the Exoplanet Program? What happened? I went forward, went backward. There we go. So there are things that are not in the Exoplanet Program. Let me make sure you know the boundaries. So first of all, Hubble is not an exoplanet-specific mission. It does astrophysics in a wide range of areas. So that's run out of STSCI, and they do great exoplanet things. I'm very excited that Hubble approved its largest ever exoplanet observation program this past year, a 500 orbit program, even larger than any cosmology program that was selected in this observing cycle. Spitzer has been located for a long time here in Pasadena at IPAC. There are also grant programs that are located at NASA headquarters, and they are not part of our office. And the TESS mission upcoming is going to be very exciting. That's run by the NASA Explorer program, not us. And JWST, like Hubble, is a general community telescope being run at NASA headquarters and STSCI. So these are some more general purpose things, including the Explorer program, that don't happen here. But let me tell you what does happen in the Exoplanet program. So the first thing is some operating missions like Kepler and K2. In order to, we manage those to make sure that they're producing their science results. Then missions that are coming, like WFIRST, which you'll hear about later today, are also managed by our program office. Concepts for future missions, I'll describe these a little bit further. We've done those in the past. We'll continue to do them. Then there are ongoing research projects that astronomers need access to telescopes for exoplanet work. NASA has supported a general community access to Keck for a long time. That's also run out of NEXI here in Pasadena. A couple other ground telescope things I'll be mentioning as I get a little further along here. And then technology development to make that coronagraph capability I showed you earlier possible. That's funded and organized out of our office, and this is the high contrast imaging testbed vacuum tank here. Then all the NEXI does, including running these workshops, is part of our program umbrella. And then lastly, there's a lot of public communications. I hope you've seen these exoplanet travel posters about Kepler 16, where your shadow has company. They're all over the place, it seems. You can download them at our website. There's still a few copies in a vault somewhere up at JPL. They've been very popular. All right, so now we'll go through the program elements. You heard from Tim Morton on Wednesday about the method he used to go and validate another 1,200 Kepler exoplanets. So Kepler is closing in on the end of its main mission. This is Kepler, not K2. So they've delivered their light curves from the main part of the mission to the archive at Space Telescope. They are working on the final occurrence rate products to be released next year. And so then the Kepler Prime mission, which ended when the reaction wheel failed, will be concluded. And of course, remember that not only did Kepler have a big exoplanet impact, but it also did all kinds of other stellar variability and other astrophysics. This is an actual observation here of a supernova event taking place in an external galaxy. And then what you can see is this little blip that takes place as the supernova is rising is thought to be the shock breakout, where the actual shock wave is breaking through the photosphere of the star. It's predicted and was observed for the first time. So Kepler has been a very broad-based mission. So the K2 mission, Kepler's successor with ecliptic fields only visible. There's been a lot of things happening there. You've heard about on the posters and during the meeting. Our office is managing the Kepler 2 mission. The data releases have taken place all the way through Campaign 8, the microlensing campaign, Campaign 9, finished recently. The data release will happen in September. There was a glitch for Kepler back in April where there was a single event upset. That's a cosmic ray particle hitting a critical part of computer memory and causing the computer to go wonky, the spacecraft to go into emergency mode. So we were a little worried for a couple of weeks back in April, but that was recovered very nicely, so still going fine. And the exciting thing about the K2 results is that there are habitable zone planets that have been found that are suitable for atmospheric characterization. And actually, Hubble is going to give that a try this year, although I think JWST will really be needed to do it properly. So the community support part of EXEP is really the heart of what the Exoplanet Science Institute does. If you haven't been there before, I really encourage you to go to the NASA Exoplanet Archive that's located at this web address, because this is sort of our official curated web page showing the detected planets and the planet candidates, not only from Kepler, but from ground-based radio velocity, microlensing, et cetera. So there are other community websites that do this, but this is the one that we're using officially within NASA. And among the things that are supported at this website and at NextSci is a follow-up program which organized the follow-up effort for Kepler so that we could tell that some stars were contaminated by companion objects, diluting the transit signal. And it's been an infrastructure so that people doing K2 observations could share their data, and it will also be that for the TESS mission coming up. So this is to enable the community to get the most leverage out of these missions along with the prime science team. So I hope you are thinking of applying for a Sagan Fellowship. Chaz mentioned on the first day. It's been a really successful program for EXEP and NextSci. There are many very promising young folks here. At least a couple are in the audience here who have been selected over these past years and are moving on to important roles. It's great to see them succeeding, and I hope you will consider joining them. The application deadline is coming up in November. So now here's a new element that's being brought into the program just this year. The Keck Observatory has 1/6 of its time for NASA, and we make that available to the entire community to propose. There is an RV instrument there, high res, that's been around for a long time, since the 1990s, and isn't doing as well as the European HARPS RV spectrograph. So the decadal survey in the US asked for NASA and NSF to make more investment into radio velocity observatory capability for the community. And so it took a while, but we finally responded to that with a proposal call for an extreme precision radio velocity spectrometer. NSF made available 40% of the time on the 3.5 meter WIND telescope in Tucson. So there was a competition to build the instrument. It was won by Penn State. The name of their winning proposal is NUID. They pronounce it that way because it's apparently a Native American word that actually means something to the people who spiritually live on the mountain in Tucson. The PI is Suraf Mahidavan at Penn State. And so this will have a visible wavelength capability at R of 100,000, and it'll be open to the whole US community to apply. So you don't have to be an insider at a big observatory that has a private user base. This is the national community, additional follow-up capability for TESS, for K2, for Plato someday, and hopefully also making preliminary observations for things like the WFIRST mission. All right, so the technology part of the program. Back in the decadal survey in 2010, NASA's #1 assignment for a medium-scale space mission was to advance the technology, making exoplanet, habitable planet detection possible. So it's a major charge to the Exoplanet Program. So how do we do that? One way we do that is sponsoring a competed proposal line where folks who have good ideas for how to make the technology better for high contrast imaging, for starshades. In the past, it was even including detectors and telescopes. People can propose and receive awards. And so if you can look here, you can see the various technical areas that have been supported. Testing of deformable mirrors, which proved to be essential for eternal coronagraphs. External starshade, mechanical studies. Being able to do mass measurements with an astrometry mission. We had one in the 2000s, SIM. It's been discontinued, and we've got to start over again. additional Starshade formation flying activities, coronagraph technology advancement, and there were proposals that were submitted back in March, and the selections should be coming out soon. So if you are an instrumentalist, our TDEM program, Technology Development for Exoplanet Missions, is something you would be interested in. So then the program also sponsored in 2013 to 2015 two probe scale mission studies. A small scale mission, less than $1 billion. $1 billion still sounds like a lot, but to NASA that's a smaller scale mission. And one of them was for an optimized internal coronagraph called XOC. The other was for a formation flying Starshade mission, and that was called XOS. And so these two studies help define the technology goals that we should be pursuing. This dedicated small telescope was Kepler-like, a 1.4 meter telescope, and would have been able to do radio velocity planets, dust disks, and some small planets. The Starshade mission, if it was made separately as a Starshade only to rendezvous with the upcoming WFIRST mission, would not only do RV planets and disks, but it could do small planets down to Earth analogs in a couple of systems. So this is a near-term way to grab some Earths, but not in a large sample. So those two studies, I think some of you have at least heard about the concept of the Starshade. Instead of putting a little tiny occulting spot inside your telescope and your instrument, you put a 30-meter scale occulting spacecraft, something like 20,000 kilometers away from your telescope, along the line of sight to your target star. And the planet is off to the side, and so its light can get around the Starshade. The star is occulted, with the shape of the Starshade being very important for the diffraction pattern to cancel out in the shadow. And this allows you to look in very closely to the star more easily than you can with the internal coronagraph. But you have to be able to position the telescope very precisely in the shadow. So what are the technology requirements to be able to make the Starshade work? So there's quite a list that's been compiled, and some of these are being worked on and others not. But one of the issues is, for example, you've got the Starshade lined up with your target star, but the sun is off to the side somewhere, and the sun is going to hit the edges of the starlight. The sunlight's going to hit the edges of the Starshade and make some glint there. So to be able to manufacture the edges of the Starshade to be sharp enough so that they don't scatter lots of sunlight into your telescope beam, that's a technology challenge that is high on the list of things that needs to be solved. So then also formation flying. Inside the shadow, you need to keep the telescope positioned to within about 20 or 30 centimeters of the center of the shadow. So if it drifts out, you've got to correct that and go back into the center. Then being able to deploy this large structure, that's a challenge. And the central disk here is also a separate deployment. That's a challenge. So there's many things that need to be worked on. And so these goals are something we're trying to support progress on. Then for the internal coronagraph, you need two things. You need masks in the focal plane to block the starlight, but that only kills the diffraction part of the problem. There's also imperfections in the wavefront. You can't manufacture a mirror for a telescope smooth enough to make sure that all the light is focused on the occulting spot. There are ripples in the mirror surface. Those ripples correspond to light that's not going to focus on the occulting spot, and so they're going to produce starlight that will confuse your planet. But if you use a deformable mirror, you can correct that wavefront like a ground-based adaptive optic system at levels of lambda over 1,000 and be able to get the contrast you need. And so the coronagraph has many technology requirements too. Fabricating these masks, this is a vector vortex mask, this wavefront sensing and control to keep the wavefront corrected, other issues like making bigger deformable mirrors, and then detectors that have very low noise. You'll see in a bit why that's necessary. And that's also needed for the Starshade, by the way, the low noise detectors. All right, so the technology program that we've been running over the past 10 years has made it possible to add a coronagraph instrument to WFIRST. WFIRST is the #1 recommendation of the 2010 Decadal Survey for Astronomy and Astrophysics. It's supposed to do exoplanet microlensing and dark energy measurements of cosmological fields. But we were able to add a coronagraph to the mission in 2013, and the mission has actually entered development last February. It's a line item in the NASA budget now, headed for launch in 2025 or so, and the science working groups have been established. So this is now becoming a real mission. So it will be able to do this exoplanet imaging in the way that the EXO-C dedicated small mission was thought, but instead of flying a separate mission for almost $1 billion, the coronagraph instrument here will be added at a much lower cost. So not only is the coronagraph on there, but there's a study going on to see if a Starshade could be launched a few years later to rendezvous with WFIRST. And so NASA headquarters has actually directed the project, go and investigate what it would take, what modifications are required to the spacecraft if you want it to formation fly with the Starshade. And next year, when the answers to that are known, we can decide if we will make those modifications. It's still not a commitment to build a Starshade. Only the decadal survey representing the whole national community can make that decision. But we want to at least make sure that this telescope is ready to fly a Starshade if the 2020 committee decides to. Okay, so the Starshade has a lot of other issues because it's not something that you can test the way it is operated in space at a 20,000 kilometer baseline with a 34-meter free-flying structure. You can't test that in the ground in any way at all. So we need a strategy for showing that this could actually be made to work without a full-scale test. So we have a strategy group that's been working since the spring, and it'll deliver a strategy later on this year to describe how we think we should proceed if we're going to make this Starshade, ready to fly for the 2020 decadal survey to choose. And so then in addition to developing a strategy, we also need to keep the technology going, and we could just let community members propose, but we need a more focused effort if we're actually going to be ready by this deadline. And so these issues I went through earlier about getting the system ready to deal with the glint, the precision formation flying, and so forth, this is something that NASA is going to make a directed effort in involving community members. So our office is organizing that. Well, if we have a 12-meter telescope, something very large in the future for exoplanet imaging, it's going to have to be segmented. We can't launch something that large with a single monolithic mirror. So there are unique problems to segmented telescopes for high contrast imaging. The segments can be misaligned in piston, they can be misaligned in tilt, and so that poses extra problems for high contrast imaging. So we had a workshop this past spring that considered all those issues in detail, in addition to manufacturing and deploying the segments. And so this is something our program does from time to time, is sponsor technical workshops with the community to help make progress on key issues. So then another issue that is important is the planets are not floating out there by themselves. They are in a planetary system that has dust. We have the asteroid belt, asteroids colliding with each other, generating dust particles. Dust particles scatter light. The dust in the ecliptic plane of the solar system is actually 1,000 times brighter, integrated, than the Earth would be in reflected light. So the dust can be a very significant background. So we need to measure that dust and make sure it's not overwhelming. What if the sun was a very unusual star and all the other ones had 1,000 times as much dust or 100 times? That might completely kill our dream of imaging and spectroscopy of Earth-like planets. So the Large Binocular Telescope in Arizona has an instrument that nulls the two beams of the 8-meter telescopes together and lets you see the extended dust at 10 microns around them. And so back in 2015, it demonstrated the sensitivity to 15 zodies on one star, but we've been stymied by technical and weather problems in the past year. So we're going to have to go and replan this effort, and NASA headquarters is deciding how we can get more results out of this that we need in time for the decadal survey. All right, so finally, if we're going to have a large mission to get that New York Times headline and to answer our science questions, then we need to start developing it, the concept of it now. We've been through this a couple times in the past. We're doing it again. And so the kind of things to realize here, this is just my own calculations of the kind of the trade-offs that happen as a function of the telescope aperture size, knowing the targets that we have out there for imaging, the Hipparcos star catalog. And so a smaller aperture, 4 meters, and that's not small. Hubble's 2.4. Okay, but if you're only a 4-meter telescope, you don't get to a lot of habitable zones. At least the 1 AU Earth, if you do a little better than this, if you were going to 1.5 AU, the outer edge of the habitable zone. You do much better if you're an 8-meter telescope, you can access this many systems, and if you're a 12-meter telescope, you could access that many systems. And then you can't necessarily get the whole spectrum because you might be able to see the visible wavelength part easily, but the infrared maybe not. And so you can see the trade-off. So what should we do here? A smaller telescope is much more technically achievable, but it has a smaller yield. And a large telescope would be great, but we are much less ready to do that. Remember that the largest telescope on the ground right now is still only about 11 meters. So launching a 12 meter is bigger than anything we have on the ground. So what should we do going through in the future? The community has decided to study two options, sort of a modest one called HabEx and a go-for-broke one called LUVOIR. And so these studies have just started up. HabEx is going to really focus on exoplanets and do some general astrophysics as best it can. JPL is leading that study. LUVOIR is to try to do Hubble with a 12 meter or bigger aperture. NASA Goddard is leading that, and it gives equal priority to exoplanets and general astrophysics. So these are likely to differ in how technically ready we are to do them, how much they're going to cost, but the studies have just started, and their goal is for these two studies to provide inputs by 2019 to the US Decadal Survey so it can decide which way to go. And so the science for these is kind of what you would expect. Do the exoplanet stuff for HabEx here, and then also do a range of general astrophysics. Then for LUVOIR, it's going to build on this report that some of you may have seen, the Cosmic Burst to Living Earth report. And it's going to do exoplanets and cosmic origins things in equal measure. And the capabilities of both of these missions are not defined yet. The science teams are in the process of doing that. I can't show you a picture of what either one looks like because the committees are defining them. But LUVOIR would like to be a very long-lived observatory serviced by astronauts in the Hubble sort of mode. All right, so I'm going to end here by just summarizing some places that you should look for information on the program and the major activities I just talked about. So first of all, the main program website is now called exoplanets.nasa.gov. If you remember planetquest.nasa.gov, that's history now. The Exoplanet Science Archive at NextSci, I hope you'll all be visiting that and making use of it if you're not already. The WFIRST project, you can follow their development of their science plans here at the Goddard website. And the HabEx and LUVOIR mission studies, their locations are listed here. Now, if you're interested in being more involved in the Exoplanet program, hearing what's happening on a continuing basis, I invite you to come to the AAS meeting a couple days beforehand. We have an activity called the ExoPag where the community meets and can give us inputs. The next one is in Dallas, Texas at these dates. And there's a whole bunch of conferences that the program has one hand or another sponsoring. Upcoming microlensing conference, a K2 Kepler science conference next June, and another WFIRST community science conference at the end of June. So there's a lot of ways to be involved in the program. Please talk to me today or at lunch. We're building these telescopes, making it happen for you folks. You are going to be the ones who will be the frontline scientists who will use these observatories, so we'd like to know how you think it should go. All right, thanks. Favorite project? Well, the real ones are the best instead of the ViewGraph ones. So, Hubble and Spitzer have done great exoplanet things, and they're for real. I think we should all be primed for JWST. We'll do imaging as well as the transit stuff. But this goal of exoplanet direct imaging for habitable planets is just very compelling. It's something that I'll work on myself even if I don't get to do it myself. You folks will do it. That's for the Decadal Survey to decide. I mean, HabEx wouldn't be cheap either. LUVOIR would probably be something approaching the cost of JWST. The community may decide that we don't want to do this, that we want a mixture of smaller things. We could end up postponing this goal by another decade. So I think both of these study teams have a challenge to produce a really compelling story and show that it's doable at a not break the bank cost.
Do any of these designs need another rocket to launch them, or are they being designed based off of what SLS will hopefully be able to do?
So both teams have to, yeah, so the idea is, will we rely on a rocket that hasn't flown yet as the basis for either the HabEx or the LUVOIR missions? And so each team has to decide what they want to do there. I have seen designs at the lower end of the size range, like a 9-meter design for At Last, which was something we looked at 5 years ago. It's very similar to LUVOIR. A 9-meter would actually fit wrapped around inside the fairing of an existing rocket. But the 12-meter probably wouldn't. We might need something bigger there. And so I think it's likely that each team will offer a design where an existing rocket could be used, and then if the SLS goes to completion and works well, how that would, like for example, HabEx is likely to want to use a Starshade. If we have the SLS, we could launch the telescope and the Starshade at one time. It would probably require 2 launches on a smaller rocket.